Thank you very much. So far it's been a great meeting. A lot of friendly colleagues. Thanks to BIMIDI and org for organizing this. So I'm going to talk about invariant foliations and why I think that you should use them in certain cases, obviously. So the first advice I got from my son about this talk is that, Daddy, please don't make it boring. So that's why. That's why I changed the title a bit. All right, so there we go. So I assume a deterministic process. That just simply means that there is some underlying map that we don't know, and that brings initial conditions to some predictions. And we have lots of initial conditions and lots of predictions. So we have exactly capital N number of them, so that these x1s are mapped to y1, x to y2, and so on. So if you look at this basketball as it flies, obviously when it's being thrown, that's one initial condition, x1, y1. And then you can then obviously subdivide this trajectory even further, and then this becomes x2, y2, and then x3, y3, and so on. And so you can see that this is my deterministic process, and obviously these people try to make sure that it's not quite deterministic that it goes in. Anyway, so I want to somehow classify data-driven modeling approaches, and I came up with a number of classes. So there are ones that can identify full models, and we've just heard one before and I forgot, right, to write it down. Volterra series can do that too. But the classical ones are regressions using polynomials, neural networks, and so on. Those are regular ones. Also, you have sparse regressions. You can, for example, the Cindy, or you have, if you have very little data, we've heard about that today as well, then you can do compressed sensing, right? And the other one, which some people call reduced order modeling, but I would be a bit more specific about it, is called, I call it manifold learning, when obviously the data is embedded in a much higher dimensional space than the model, and hence the data is on an invariant manifold somehow. So here, these blue dots are mapped into these purple triangles, and if you have a linear manifold, then you can do PCA. If you have something nonlinear, you can use an autoencoder. In fact, that is the nonlinear generalization of PCA by Kramer from '91. You can use diffusion maps, isomaps, equation freeform models, and I expect to hear about this class of methods in the next talk from Yanis. He has developed most of these. But what I really want to focus on are the reduced order models, where there's no such manifold, or if there is a manifold, the manifold is much larger than, or much higher dimensional than the dynamics you want to extract. So you can imagine that you have something like this type of a dynamics, and you want to make order in it. So instead of trying to create a map between points, initial conditions, and predictions, you should create a dynamics between sets of points, sets of initial conditions, and sets of predictions, and that's why I have these surfaces, right? So your initial condition lies, or a set of initial condition lies on one surface, and then it's being mapped to another one. And these surfaces are mapped into each other, and that makes these invariant. So this is what I'm going to talk about now. This map obviously can be nonlinear, and when it's linear, that's dynamic mode decomposition, or a Koopman mode. Right. So how do we relate data on a higher dimensional space to something lower dimensional? Or in fact, it can be a model as well. So what you can do is that try to connect the initial conditions and the predictions to the initial conditions and the predictions to your lower dimensional model. And obviously you can do it in one direction from the high dimensional to the low dimensional, or the other way around, from the low dimensional to the higher dimensional, right? And then once you have these two choices, then you can create 4 combinations of these and then investigate what is going on. All right, so let's go into these. So obviously I will start with the invariant foliation, which is my favorite. It is basically consisting of an encoder. So we are going from high dimensions to low dimensions, and this dynamics, if it commutes, then this invariance equation holds. The nice thing about this one is that you can plug your data directly into it. So because your system creates this yk, normally this would be f of xk, but you can replace it with yk. And you can feed this directly to your data, basically, the R and U, where U is the encoder. The other one, which is also invariant, the invariant manifold. And this is what you do when you have an equation, and you want to calculate an invariant manifold. And in this case, you use an immersion or a decoder in computer science language, which connects the low dimensional space to the high dimensional space in both directions. And if this dynamics commutes, then you have this invariant equation satisfied. But you cannot fit this to data because there's no data anywhere in this equation, right? You cannot actually, but if you have an offline system, then you cannot actually make this F perform this mapping from WZ to something, right? So that's just simply not possible. All right, so we have the autoencoder, which is very nice because it can identify invariant manifolds. And this works by using an encoder and then a decoder, right? And this is very nice because first you can pre-train that the W composed with U is nearly the identity. And then once you figured out your W and U, you can use the invariance equation to figure out the low dimensional dynamics, right? But if you have a dynamics that is higher dimensional than what you have assumed in R, this cannot guarantee invariance. So you might get spurious results. And the way you can check that is if the W composed with U is not the identity, then you are in trouble, right? The fourth one is the equation free model that Yanis came up with. And in this case, we first, for the initial conditions, we use a decoder. So that's a manifold immersion. And for the prediction, we use an encoder. And this works when you can run lots of small micro simulations, but you still have an invariant manifold somewhere that the simulation itself will always converge to that manifold, right? And in this case, you can pretty much choose any U and W, and you get your reduced order model from that invariance equation. All right, so what I didn't tell you about, but you already know that obviously the autoencoder can also be fitted to data. But we can characterize these 4 possibilities into which one is a reduced order model, right? Well, the reduced order model is an invariant manifold and the invariant foliation in the sense that it gives you invariance and reduces the dimensions. But there's another set which can be fitted to data. The foliation and the autoencoder can be fitted to data directly. And when you have the intersection, that's just the invariant foliation. So this is hopefully convincing you that when you need to actually reduce the dimensions, you should use foliations. Equation-free model, as I told you, it's good for a number of cases, but it's neither one of these. All right, so what does an invariant foliation do? So I talked about the functional representation of an invariant foliation that consists of a function u. It's actually a manifold submersion, or I call it encoder. And each level surface of this encoder or manifold submersion is called, each constant level surface is called a leaf of the foliation, right? And geometrically, the dynamics then maps these leaves into each other, right? And then you can do this in different directions in your system. So for example, you can do on these surfaces, but you can also do horizontally along these lines, and there are two different invariant foliations of the same data set. And if you are then doing it carefully, that the codimensions of these two foliations add up to the dimension of your data, then you can uniquely track, using those two foliations, your trajectories. So these intersection points then of these lines and surfaces will be actually the trajectories of your dynamics. Another thing about this one is that once you have a stationary leaf, that is an invariant manifold, right? Because it's being mapped into itself. So you can actually calculate invariant manifolds using invariant foliations. Okay, and obviously this is the geometry of it. And if you want to think about it a bit more philosophically, then you can think of the encoder as a measurement, if you're a materialist, right? And or if for an experience, if you're an idealist. But that's for another audience, I suppose. And foliations can also capture multiple attractors at the same time, just because the underlying dynamics is nonlinear and can itself have multiple attractors on the lower dimensional space, right? Right, so there's some theory to it. So in terms of the autonomous case and around a fixed point or equilibrium, and under certain non-resonance conditions, there exists a unique invariant foliation. Now, this theorem is valid in certain classes of function spaces. And because invariant foliations are generalization of Koopman eigenfunctions, this will actually tell you about the uniqueness of Koopman eigenfunctions as well. You can also do the same thing for a forced case. So you can see this skew symmetric dynamics where you have a map and that's being forced with the dynamics on a d-dimensional torus. And in that case, you have the exact same statement, but now the foliation is about an invariant torus. So in mechanics where I'm working at, basically we tend to reduce things into two-dimensional manifolds where we have oscillatory dynamics. So that's what dynamics in mechanical engineering usually does. And in that case, the normal form of any of that oscillatory dynamics is just these two equations, right? And you can even do that for the forced case under some non-resonant conditions, so that your dynamics looks like this in a certain coordinate system. All right, so what do we do to identify invariant foliations? So first, we need to find an invariant object. So that's either an equilibrium, a periodic orbit, or a quasi-periodic orbit. Then we need to estimate the linear dynamics about the invariant object, and then select an invariant vector bundle or subspace. And in fact, it has to be an adjoint subspace because it's a foliation. And then we have to initialize our foliation using this selected vector bundle and then minimize the residual of the invariance equation, right? So then you can see that there's a choice here in terms of which vector bundle you're choosing. and that will tell you what is resolved in your foliation. And you can make different choices, and then you can resolve the whole dynamics if you want to, with many foliations if you like. Right. And if you also want to find an invariant manifold, because why not? Sometimes it's very helpful to have an invariant manifold. Then you select the complementary invariant vector bundle that is complementary to the one that you've selected here. So it's much higher dimensional, obviously. Repeat number 5, but since you are finding an invariant manifold, this R can be actually linear, because we are only interested in a neighborhood of an invariant manifold where this U is very small, right? Because the invariant manifold is a 0-level set of this U. So in this case, when this U is small, R can be linear, and this is actually becoming much simpler. That's actually a Koopman eigenfunction. Right. And if you've done it right, then you corrected your invariant, the prediction for your invariant torus, because that's in the intersection of the two invariant manifolds defined by the 0-level sets of your foliations. Right. So how does it look like in the quasi-periodic case? So I've told you a number of steps, but in fact, a number of them can be compressed together, right? So it doesn't actually have to be that tedious. So what you do for linear model identification is you try to fit a model like this to your data, and that will give you both the invariant torus, because that is just a stationary solution of this forced equation, right? And the vector bundles can then be calculated from this A parameter dependent matrix, or like, yeah. And then once you figured out those obviously invariant vector bundles, then you can then solve the invariance equation. So in terms of geometry, this is how you should think of it. So the leaf of the foliation that goes through your invariant torus is actually the invariant manifold. But there are many more of these leaves that are parallel or nearly parallel to it, right? That being mapped into each other, and then these leaves fill up a sizable neighborhood of your torus. So it's a non-zero measure about your torus, right? Okay, so how do we calculate invariant vector bundles? The invariant vector bundles basically are just invariant subspaces along each point of your invariant manifold, and they are being mapped into each other. And I think this is the most delicate problem in this identification process, because you will have a spectral problem from which, when you discretize, you get a lot of spectral points, but you just don't know which one to pick in order to figure out an invariant vector bundle. And that is tough. So what I do is that I choose the one with the smallest total variation, so that when you have multiple of these invariant vectors, they don't intersect each other as they rotate around your torus, right? And hopefully that is working, right? And also, in order to represent this foliation for a high dimensional data, I have to somehow represent the function u, and I use a polynomial that has obviously tensor coefficients, and these tensor coefficients are compressed tensors. And I really don't want to go into the detail of this because I don't have much time, but you can definitely ask me about it later. This is a very well developed theory. People don't really talk about this anymore just because it works. Right. So I did a tabletop experiment, and I think this is the fun part. So what I did is that I took the kids' crafts table, yeah, one of these floorboards, a little piece of my dishwasher, and drilled holes to it, put a lot of bolts in them, just to make sure that the frequencies of this is quite low, so that my camera that is usually bolted on my bike can, thank you, can actually capture the vibrations. And I also mounted some exciters. These are Dayton audio exciters. You can buy it £5 a pop. I actually burnt one of them just when I tried them and recorded some vibrations. What I've done actually, these are these bolts. I hammered on them and recorded them with the camera. So what I got out of this is actually quite remarkable, given that the vibrations are actually pretty low amplitude, and I could resolve them to 1/50th of a pixel, which is great. So when you don't put forcing in, then you get basically about 2 pixels large vibrations, but that is quite lucky because the noise is about 1/100th of the maximum amplitude. Unfortunately, there's trouble when you have low amplitude vibrations. And then I also have a forced data, and these are the spectrograms of these trajectories. I created a lot of trajectories. Each of these bolts were hammered on 3 times, and I tracked these little bolts under them. So those were 18 of them. So I had about 400 and something trajectories to analyze. Right. And what I've done is that exactly the same I just told you before, is that first I identified a linear model about an invariant torus. Well, in this case, it's a periodic orbit, but the sampling rate is not the same, or actually rationally independent from the frequency. So that's why it looks like as a torus. Calculated the spectrum, selected the one that I'm interested in, the ones with the slowest decay, for example, here. Calculated the vector bundles, and these are some coordinates of the representations of the vector bundles, how it varies along the torus. You can see some variation. So that's all you need to know about it. And then ran the fitting process, fitting the whole foliation to the data, and also calculated an invariant manifold that was in 0.6. And as you can see, in this coordinate system, obviously there's an invariant manifold, or at least a cross-section of the manifold at each point of an invariant torus, and this is just one of them. Right. And I did it for the second frequency as well, which has a much bigger decay rate, and the invariant manifold is a bit better there. But what we mechanical engineers are really interested in are the frequencies and damping ratios, and that was summarized in that 2-dimensional model. Thank you. So what I've also calculated is for first frequency, I calculated how the frequency varies with respect to the amplitude, and how the damping ratio varies with the amplitude, and so also for the second, for the forced and the unforced case. I did the same thing for a traffic model, but as far as I can see, I don't really have time to go into that, and that's that. Thank you very much for your attention. I have to tell you conclusions, right? At least that. So only invariant foliations can capture reduced order models. That's my statement. You can probably disagree with that. Dealing with exponential dichotomy, or at least finding invariant vector bundles, is the hardest part of this process. Once you've done that, actually these get corrected in the fitting process. So don't worry if you didn't get them right for the first time. And the distribution of data does matter, especially when you have noise at low amplitudes. All right, nice. Finished. Thank you very much.